Thank you for attending Questline Academy webinar, RTU and Chiller Maintenance for Maximum Efficiency. My name is Christina Harum, and I am the host of today's webinar. We will be sending everyone a follow-up email within the next couple of days, and that is going to include a PDF of the PowerPoint presentation materials and the playback link to the recording of today's webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All of the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you do have any questions during the webcast, you can submit them through the Q&A widget. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, we will answer that later via email. Some networks do cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. You can find additional answers to some common technical issues located in the Webinar Tips and Help widget at the bottom of your screen. We will be conducting polls during the presentation, and we would really appreciate your participation. I'm going to go ahead and open our first poll now. Please be aware that you are not the only participant today. The names of the other attendees are not being shown for your privacy. So now, let me go ahead and introduce today's presenters. Mike Carter is a senior engineer for the Questline service. Mike has a BS in engineering and an MBA degree from The Ohio State University. He has worked with various EPRI centers supporting electrotechnology applications and spent 10 years conducting due diligence for technology commercialization. At Questline service, Mike writes articles for the newsletter, answers Ask an Expert inquiries, and develops webinars on energy topics. Jason Whitman is the Senior Energy Efficiency Program Coordinator for Indiana Michigan Power's commercial and industrial customers in Michigan and has been in this role since May of 2016. He has a BS in Computer Information Systems from Colorado Christian University. Prior to joining the energy efficiency team, Jason worked at Indiana and Michigan's Cook Nuclear Power Plant for 5 years as an instrumentation and controls maintenance planner, and for 13 years in the U.S. Air Force, serving as a nuclear weapons launch officer and data and technology acquisitions officer. And now I'll go ahead and turn it over to Mike, who will get things started for us today.
Well, thank you, Christina, and welcome everyone to our webinar on HVAC maintenance today. This is part of a series of webinars that Indiana and Michigan Power is offering its customers to help you better operate your facility and decrease your utility bill. We spoke on the subject of building automation last month, and the next month we're going to tackle electric vehicles, and followed by, in July, giving you an overview of Energy Star Portfolio Manager, a great tool for benchmarking your energy performance and tracking that over time. But today we're talking about maintenance and energy efficiency. What do those two things have together? Well, I think it's best stated by Robert Baker, who's chair of ASHRAE's Standard 180 Committee, which is the standard practice for inspection and maintenance of commercial building HVAC systems, a great resource for you. And he said, and I'll quote, "Where maintenance is neglected, energy costs rise significantly and equipment life drops dramatically. With HVAC systems responsible for about 60% of site electrical energy use, it's imperative that we provide consistent maintenance and inspection to improve energy efficiency, along with thermal comfort and indoor air quality." I think he says it well. And so today we're going to talk about just the concept of maintenance, different types of maintenance. Then we'll look at RTU basics, RTU maintenance, chiller basics, and chiller maintenance as well. So with that, let's get started and talk about some of the basics of maintenance. Now, you've probably heard the different kinds of maintenance: proactive, preventive, predictive, reactive. And reactive maintenance is defined as repairs made only when there's a failure. So this obviously results in short-term cost savings, but can result in great discomfort to building occupants. Proactive or preventive maintenance is a time-based approach. So you schedule certain repair or replacement activities over the life of a RTU or chiller. And probably the better approach is predictive maintenance. And predictive maintenance anticipates probable failure before problems arise. And it's good in that case to use log books to track some critical predetermined operational metrics, things like condenser coil cleanliness, condenser fan operation, refrigerant charge levels, etc. In addition to that, real-time monitoring has contributed greatly to the ability to review and respond to changes in your chiller or rooftop operation and overall process performance. When you do that, operators can compare, say, past baseline results against current readings to determine if there's a problem that might be cropping up in the future. So, what are signs of maintenance issues? Well, if you look and you listen, you're going to probably see many of these: the corrosion, leakage. You'll hear excess noise or vibration, worn or damaged installation, etc. So these are just a few of the things that's going to give you an inkling that, hey, there's some maintenance issues we need to address. And then when you run into these problems, I just came across this great root cause analysis methodology from Mark Org. It's a root cause analysis to building operations, and it kind of helps you figure out, well, what's going on wrong here. And I call it the 6 M's. It could be something to do with man, method, machine, materials, measurement, or even Mother Nature. And it's a great methodology just to start with the top and work your way down to kind of figure out what's causing our maintenance condition here. And I'll be glad to go into greater detail if you want at the end of our presentation. You can type that in your Q&A text box. So our second poll for today: how is RTU rooftop unit or chiller maintenance conducted at your facility? Is it done by internal maintenance staff? Is it done by an outsourced contractor? Or do you really not have a formal HVAC maintenance plan? So I appreciate if you could jump on that, give us your feedback. We'll look at the results of that here in just a little while. And while you're filling that out, we'll go ahead and move forward and start our discussion of packaged rooftop units. And just what is a RTU, as we call it? Well, ASHRAE's definition says it's a unitary cooling equipment, one or more factory-made assemblies that normally include an evaporator or cooling coil and a compressor and condenser combination. And the units can perform a heating function as well. And you'll see that here in the different pieces, parts that's inside this package unit. It's often just lifted up on top of the building. It's interesting that 1/3 of all commercial buildings have packaged rooftop units, and that represents cooling of 50% of commercial floor space. So they're pretty darn ubiquitous. I'm sure many of you have those as well. And what impact does good maintenance have on rooftop performance? I'm glad you asked. There's an interesting longitudinal study of rooftop units not too long ago, and it was conducted by Advantech Consulting, Michael West, and Richard Combs. And they came across a mall constructed in 2003 in South Carolina that had 11 rooftop units, totaling just over 200 tons. And the area served by one particular rooftop unit was a large open retail space that had high ceilings, subject to frequent door openings, and which in and of itself provided some uncontrolled but pretty effective fresh air ventilation. And when they first evaluated the unit 7 years after installation in 2010, this particular RTU unit had been in operation and had an integrated energy efficiency ratio of about 7.8 million BTU per hour per kilowatt, which is 30% below its factory ratings. You can see the degradation over about 7 years without any maintenance. Of course, power demand had also climbed by about the same percentage from 23.7 kilowatts up to about 30 kilowatts. And so what they did at 2010 was they instrumented this unit with about 45 refrigerant and air sensors and web communicating data loggers. And they monitored it for several years. And then during the 3-year period, and we got our results back here, so it's kind of split. Your chiller maintenance being conducted, about half of you conduct, if you do the maintenance internally, and half of you outsource it, and a few of you don't really have any formal maintenance plan, which hopefully maybe that'll change today. And anyway, they had 5 service companies starting in 2010 return the unit to good working order. The first 4 performed just routine maintenance, rinse the condenser coils, check refrigerant charge. The 5th corrected sensor wiring and switched circuits, replaced a compressor, 2 fan motors, replaced both liquid line dryers twice, removed clogged suction line filters, flushed circuits, adjusted the refrigerant charge, and cleaned the condenser and evaporator coils. And after servicing the proper way, the field measured IEER efficiency was improved from 7.8 to 9.5. So about a 22% performance improvement, and resulting in energy savings of about $1,870 per year. Now, it wasn't returned to the factory rated IEER of 11.2, and you might ask, well, why not? Well, it would have required replacement of the condenser coil and possibly the other compressor, which was deemed not cost effective. So lessons learned, basically that comprehensive preventive maintenance performed twice a year for an RTU serving a retail mall would have paid for itself, along with a 50% ROI over a 15-year life cycle. So the preventive maintenance costs over 7 years of the life, if they had done it, would have totaled about $5,600 as shown here. And by deferring maintenance, though, assuming straight line depreciation and performance, the added energy costs would have been was actually $8,400 over those 7 years, and would have added up to $15,000 over 12 years, and a decrease in the rooftop life of about 3 years if nothing had ever been done. So, and obviously you would avoid occupant complaints as well, which sometimes is the primary interest of a lot of facility managers. So good feel for significant impact by poor maintenance on performance. So what can you do in terms of preventive maintenance priorities? Well, here's a minimum of at least 9 things here. Clean the condenser coils, make sure the fan's working, get the right refrigerant charge, verify proper economizer operation. That's really interesting. I take classes occasionally with HVAC suppliers, and I'm in the midst of a bunch of what they call themselves wrench pullers. So they're out in the field working on these things every day, and I always ask them about, hey, how many people are using economizers? What state of operation are they in? And almost inevitably, and I just had a class here a couple weeks ago, talked to a guy, older guy who's been doing this for 30 years. He said 80% of economizers up on the roof, they aren't functioning. And it's not because they even can't. A lot of times they just were never finished installing, or there is something wrong, a linkage is broken or whatever. So it's quite worth verifying a lot of what you think should be working when it actually isn't. Now, if you want to get into more detail, here's a biannual list of things that you can do on your rooftop unit. Things like test the economizer I just mentioned, check refrigerant pressures and subcool and superheat temperatures, check the amperage draw of compressors and fans compared with nameplate, etc. And then here's some things you can do on an annual basis, a little checklist. Clean the evaporator coil, inspect the condensate drain pan, clean blower wheels, etc. And so I'll leave that for you. It's something I think is very useful you can incorporate into your own program. Just a word about cleaning coils. The evaporator coil is much more sensitive to cleanliness than the condenser coils. And there's been some studies, and they determined that if the evaporator airflow is restricted by a third, capacity drops by about 20%. So a 3-ton unit would now become a 2.5-ton unit. On the other hand, when the condenser coils are 50% restricted, quite a bit more than what we gave just now, the capacity drops only about 11%. But it's still, 11% is pretty significant. Just realize that the evaporator coil is a lot more sensitive than the condenser coils. And what's a proper method for cleaning coils, particularly condenser coils? Typically it's done with wet vacuuming using high-pressure cold water. Recognize that the coils collect dirt on the side where the air enters, generally outside. And so the high-pressure water pushes dirt out the same way it came in. Now, typically you want to do this using professionals because those aluminum fins bend pretty easy if you spray at the wrong angle. And sometimes hot water and steam are used to clean coils. Generally, surface dirt debris can be removed using a stiff bristle brush or wire brush. A lot of companies use biodegradable detergents as the safest coil cleaners. However, sometimes you have to go to higher strength alkaline or acid cleaners. And so it needs to be done, and it needs to be done right. Hiring a professional is probably a pretty good idea. When you're looking at fans and belts, this is a pie chart showing sources of drive problems. This was collected by Gates Corporation, who provides pulleys and shivs and belts and etc. And note that improper drive maintenance, no retensioning, not replacing a worn shiv, not cleaning the guards, etc., not checking alignment, is really a third of sources of fan drive problems. The rest being, environmental factors or improper belt or pulley installation, etc. So maintenance has a big impact on that. And so you really want to go and check your fans, when they're off and power's off. Rotate the fan, make sure it can move freely by manual intervention. Check bearings. Loosen the belt tensioner when you're putting new belts on. Don't stretch them over the shivs using a screwdriver or whatever. And then use appropriate belt tension device, a Browning or Gates tension gauge. And you're going to have to do that when you first put the new one on, probably a couple times during the first 2 to 3 days because they'll stretch just a little bit. And you want that optimum pressure on that. Generally speaking, a standard sight glass will be available with an RTU, has an indicator with a dual function that monitors whether the moisture content of the refrigerant is within an acceptable range, and it indicates whether liquid refrigerant is always present at the expansion component. If the moisture content is okay, the indicator color will be green. You won't have to do any further action. If the indicator color, however, is yellow, that's going to indicate there's a problem with the moisture content of the refrigerant. And frothing in the sight glass would indicate either a shortage of refrigerant or that the refrigerant in the liquid line is not entirely in the liquid state. So it's a nice indicator of what's going on with your refrigerant. All right, next poll question. Which of the following is the leading source of fan drive problems? There's 4 choices: improper installation, environmental factors, proper drive maintenance, poor drive design. Which one of those did we say was the leading source of fan drive problems? Appreciate you letting us get some feedback on that. Make sure we're communicating well today. All right, we've talked about the rooftop units. Turn our attention to chiller components, chiller operation. Here you see quite a bit of the hardware associated with chillers. You've got the compressor, with the compressor motor. You've got actually 3 loops represented here. You have a refrigerant loop that's going between the 2 barrels there, the evaporator and condenser barrel, which are filled with refrigerant. And you have 2 water loops that pass through each of those as well. You have on the right-hand side the chilled water loop, and it's showing about a 40-degree supply and a 50-degree return, so a 10-degree delta there. And then you have the cooling tower loop showing again a 95-degree supply to that cooling tower and an 85-degree water return. So again, about a 10-degree drop as well. And there's a number of efficiency metrics that are important for chillers, and I've listed several here: delta T, a couple of approach temperatures, and lift. High chiller efficiency is accomplished by properly controlling a lot of energy-munching chiller subsystems like the refrigerant loop compressors, the water loop pumps, chiller evaporator fans, cooling tower condenser fans, air handling fans, and they all affect these metrics. And so, however, by improving one, you might affect the other. It gets kind of complicated, and I really want to emphasize how important and useful it is to have an energy management system that can control your chiller and deal with this. So I want to emphasize that by having us watch this short 90-second video that will explain a little bit different.
Chillers are inherently very complex, and making them efficient can be even more complex. The goal is to constantly balance the cooling tower fan speed and the chiller compressor operation while achieving the lowest kilowatt per ton power draw. There are 3 main reasons for inefficiency with chillers. Delta T is the difference between chilled water supply and return water temperatures. Low delta T forces chilled water pumps to work harder than necessary to produce the needed cooling. More energy is wasted when the operator turns on a second chiller when one properly sequenced chiller would be enough. Approach temperatures both in the condenser and evaporator are also important when it comes to efficiency. In both cases, lower is better. A 1-degree difference in approach temperature represents a 2% decrease in efficiency. Low approach temperatures are a sign of good heat flow between the water and refrigerant. The third area of efficiency issues happens when balancing the cooling tower fan speed and chiller operation as characterized by chiller lift or head pressure. Chiller lift is the difference between the entering condensing water and leaving evaporator water temperatures. Lower lift is better. The most effective way to maximize efficiency in your chiller is with an energy management system, or EMS. An EMS will constantly control, monitor, operate, and alert you to any potential issues with your chiller system. Considering the energy it could save, adding an EMS is definitely worth the investment.
All right. Well, hopefully that made the case how valuable an EMS system can be in your HVAC operations. Works for rooftop units as well, to some degree as well, and certainly for chillers. We got feedback on our poll, which the following is a leading source of fan drive problems. And hey, the majority of you got that. Improper drive maintenance is number 1. Environmental factors, improper installation, poor drive design, they all factor in as well. But the biggest is improper drive maintenance, which is, of course, the topic we're tackling today. So chiller maintenance, here's, again, at least the minimum you should do are these 5 areas. Again, we've been encouraging you to document with a log the performance of your system over time. The oil and refrigerant can be analyzed in a chiller system and give you some good information on how the chiller is performing. We talked about cleaning. We talked about leaks here already as well with our rooftop units. Of course, we have now water involved as well. So let's take a closer look at several of these areas. We'll start with this oil and refrigerant analysis. And you can see kind of a difference here in the 2 bottles, the oil, compressor oil on the left versus the right. Darker is more contaminated oil, older oil, and you want to change that at least once a year, and send fluids out, oil and refrigerant, to be checked by a qualified lab on a regular basis. Obviously, you want to look for leaks. A lot of spinning components here, so journal, thrust bearings, drive gears are important things to check out as well. On the compressor itself, you have motors, electric motors. Check the terminals, check amp draw, make sure crankcase heaters are working, and make sure that any insulation, the pipe insulation on the chilled water lines, they probably won't have any on the condenser, but chilled water lines, make sure they're dry and still there. Either were replaced after inspection or were replaced if they fell off or broke off for any reason. So, and then centrifugal chillers in particular, you often control refrigerant flow using some sort of a guide vane linkage system, kind of shown here on the right, which is fully open position there. And then reciprocating machines, you have compressor suction discharge valves that open and close. And then in some cases, you'll have, for simple refrigerant metering, you'll use capillary lines like this. That's in lieu of thermostatic expansion valves. Probably more seen on RTU units, but they're pretty long, 5 to 15 feet, very slender tubes, brazed, and with vibration can leak or crack and misfunction. So inspection of those is important too. If you look at the evaporator condenser heat exchangers, mainly tubes, things like superheat, which is the temperature after the evaporator, right before the compressor, and subcooling, which is between the compressor and the condenser. Those readings will tell you a lot about the chiller's efficiency. And then you can see here an example of how bad tube corrosion and or contaminant buildup can be. A lot of companies use eddy current testing to determine if any of those tubes are damaged, cracked, etc. And you'll have to clean these tubes either using mechanical means like brushes, etc., or in pretty bad cases you might have to use some pretty high-powered chemicals as well. In terms of the cooling tower maintenance, we went out and looked at a lot of recommended cooling tower maintenance checklists and kind of compiled our own here, the best practices of all those. You can see here's a list of over a dozen of these, and they're divided into monthly, quarterly, semi-annually, and annually type of activities. It's typically conducted during cold weather months, including often holidays, on an annual basis, and it really takes time. It usually takes 4 or 5 consecutive days. For instance, day 1, you'll drain the sump, cooling tower floor, and let it dry. Day 2, you might wash down the tower walls and filter media and then let them dry. Day 3, you might clean coils and adjust or replace fan drive belts as needed. And day 4, then you're refilling the sump after cleaning's completed and you're checking for leaks. So here's just a nice list that you can use for that. Any questions about what we're covering today, or just something that's going on with your facility from a HVAC aspect, just type those in the Q&A text box and we can address those here in just a little bit. Again, we have the water loops, a lot of water involved with chillers. You want to clean condensers. There's filter media shown here on the right. You can see how badly it can get gooped up here. Also, there's strainers at the bottom of the pan. It's trying to strain out the big leaves and dirt, etc. You have spray nozzles at the top. We'll see an example out here in a minute. That should be uniform. All the nozzles should be working. And so those are things to look at. Obviously, condenser coil cleaning, which we mentioned just briefly. Here's a good example of, obviously a brand new set, and then ones that you have scale buildup. Scale buildup can reduce energy efficiency, as shown here. And then proper water filtering is important. That's usually done one of three ways, either full stream, side stream, or basin sweeping. And there's pros and cons of that. If you look here up in the top right, this is full stream. In other words, all the water going through the tower goes through the filter. It's going to create additional pressure drop, and increase system head, but it's going to be, most effective in terms of cleaning all the water. You could just do a side stream where you take 10 or 20% of the flow at a time and filter that. That's pretty good for existing buildings. It's a lot cheaper than going to a full stream. Or you could even go and just do basin cleaning, which requires jets in the sump and removes dirt at the source. So that's pretty good for new or existing buildings. New or existing buildings. So I mentioned that cold water basin. Looking for any obstructions. We talked about keeping that strainer cleaned. Make sure the makeup water valve is working. And if you have metal, usually they're float type systems. If you have older metal floats, a lot of times those will corrode, and you're not, when it can overflow, not drain, or it could, use too much makeup water, and so you want to make sure that's working well as well. Here's a good example of the spray nozzles being. You can see it pretty much all of them are working. Look like a pretty equal distribution pattern as well. That's what you want to see. It'd be nice if you could measure pressure drops through the water loops. Typically, you're shooting for about a 15 psi differential through the water loops, and then keep chilled water flow rate between 3 to 12 feet per second, kind of a ballpark target there. I want to mention controlling Legionella growth. If you're not familiar with this, Legionnaire's disease first came into wide public notice in the mid-1970s during an American Legion convention in Philadelphia. And the situation was you had a bacterium named Legionella pneumophila, which was found in the convention hotel's cooling towers, and it ended up causing 34 deaths. Now, Legionellosis disease is not really widely discussed today, but it is on the rise in the U.S. according to the Centers for Disease Control, and it's often misunderstood. And I've heard about some Legionnaire's disease deaths just a few months ago. So it's still out there. And one of the challenges with it is it's only one of about 20 species, the particular Legionella pneumophila that was originally discovered. It's only one of about 20 species of Legionella bacteria that's dangerous to humans. But the LP, as we call it, Legionella pneumophila, it causes more than 90% of Legionellosis disease cases. Now, the exposure is most likely to occur from inhalation of either fine sprays or mists or other microscopic droplets of water contaminated with Legionella. In other words, you can probably drink Legionella. It's not going to hurt you. It's when it gets into your lungs that really is a real problem. And you typically don't see symptoms until about 2 to 10 days after exposure. So there's a number of treatment options. Very challenging thing to address. And you could either use heat, chemicals, light, ozone, or ionization. Number of techniques out there. And in terms of operational best practices, you don't want to keep water from stagnating in places. Temperature is important. Less than 65 degrees, more than 140 degrees is usually pretty safe. It's that in between that's a challenge. and you want to keep, this is an airborne type of a thing, put some physical barriers there, like a drift eliminators or mist eliminators on the cooling towers to keep that from traveling very far. And again, I can talk a little bit more about that here at the end if you're interested in learning more about that. There's airflow systems with cooling towers, and there's different methods here. You can see induced draft counterflow, induced draft with fill, double flow, single flow, and so you got fans and belts, things that you have to maintain, as I said before. All right, we talked about economizers and how often they're not operating, so you want to re-enable those that are out there. I know the latest energy codes, actually standard 90.1 energy code for commercial buildings, it now requires economizers for all rooftop HVAC in the country except for just very hot climate areas, very minority, very small. So 99% of U.S. is required now. And so you'll control that free cooling. What you do is you shut off your compressor, you open up the outside vents, you pull in outside air, which hopefully is below a certain temperature, particularly about 50 degrees, 55 degrees, and low to medium humidity, and you pull that air in, and you don't have to condition it. So it's free cooling, and you can do that based on just temperature, or you can do that based upon temperature and humidity level, which you use what's called an enthalpy sensor for that. And those need calibrated. And then there's issues about building pressurization as well. You have to make sure that you have an adequate airflow path and ways to relieve building pressure. And then there's devices out there that do a good job of that. It's important for economizers where your air sensors are located. You don't want them directly in the sun or too close to other air outlets. And you want them, when you're looking at mixed air, typically you're measuring the return air along with the incoming supply air, and you want that in a place that has good mixing as well. All right, air handlers. Outside air dampers, well, they're moving parts, they're outdoors in the weather. They can seize in place due to entering debris or humid conditions, and the linkages can fail. So you really want to cycle your dampers open and close periodically and verify that they operate as intended. This requires one person at the control system, workstation, and another person actually observing a damper operation. I have a good friend that he used to work with one of the major HVAC maintenance companies, and he said it was very common for his staff, the maintenance techs like himself, they would just look at the workstation and the computer sensors and trust that they were reliably indicative of what's actually going on outside. He himself, he said he would open the damper, ask the dampers to be open. He would walk outside. He'd check to see that they are. You can see here on the right-hand side, yeah, half of them open, and half of them did not. Stuck dampers. Also, you can have a condition like down below where you have a slight opening in the quote-unquote closed return air dampers, and a slight opening translates to a pretty significant amount of airflow. So you have to verify that they close, and hopefully you have jam seals that help as well. And so just important to check to see that what your control system is telling you is actually happening out there. I'd quoted from the person who headed up creation of this ASHRAE standard, inspection and maintenance commercial building HVAC system. So it's a great resource for you. I really encourage you to tap into that and take advantage of that. So there's a good overview of HVAC maintenance, some details on maintenance of rooftop units, some details on maintenance of chiller systems. And I'm going to turn it back over to, here to Jason. He's going to tell you a little bit about Indiana Michigan Power's energy efficiency programs, particularly as it relates to HVAC.
Terrific. Thank you, Mike. As always, excellent presentation, pretty wide-ranging. Our goal here at Indiana Michigan Power, and with the help of Mike and the Questline team, is to really educate our customers, help you improve what systems you have in place, understand what is needed for a new system, and really how to manage that. And again, a wide range of topics from rooftop units to chillers, and understanding the specifics of maintenance needed to ensure the most energy efficient use of that system. So I really wanted to take just a few moments and talk about what programs we offer. Indiana Michigan Power, our goal is to, as I said, ensure that if there's any energy efficiency upgrades that you're planning to do, that you as our customer are aware of what we have in Michigan, and as well as what we offer in Indiana. Our presentation here today is really geared and brought to you by our Michigan education program, but it's applicable to both states, all of our customers. We want you to benefit from being aware that we have prescriptive rebates that we offer. And I put a little screenshot here of our rooftop units and what we offer as an incentive. And yeah, your first impression is probably correct. It seems a little bit low for what we offer for a rooftop unit. We understand these are costly, and this is our rebate amount as we have ascribed to in our prescriptive program. The bottom part of this screen, I highlighted our custom program, and it really gave you an example of a customer who had an air-cooled chiller installed, and the initial cost, and what the incentive amount was. So you can factor in a multiplier of 6 cents per the kWh saved, and that'll give you an idea of what kind of incentive in our custom program is available for other type of systems, specifically here an air-cooled chiller installation by a customer. So the prescriptive program, we offer some limited rebate options. Again, they are on your screen here. You can access the brochure that we have and the pamphlet available on electricideas.com for those specifics. But if you have a program or a project that you're going to do that's outside of that prescriptive program, we point you to our custom program where we offer an incentive of 6 cents per kWh for Michigan. And I put in our caps there at the top too. So for 2019, our caps for Michigan are 50,000. If you have multiple sites, so that gets expanded to 100,000. Indiana, we have a much larger customer base, and so the caps are a little bit different. However, we still find that the incentive caps that we offer for Michigan and Indiana are very lucrative and offer a real opportunity for you to offset your project costs with an incentive or even a rebate from our prescriptive program. So if you have any questions, I'd ask that you address any of those via the question and answer on today's webinar, and then we'll follow up with any questions as well. Specific program questions and how to get a rebate, electricideas.com is really the source we point you to. We have program updates that we highlight there. The application is available there as well, and we would like you to really specifically go to electricideas.com/work for any of those specific questions. I hope you found today's webinar useful. I know that we have done a building automation system, and we have an electric vehicle and an Energy Star portfolio webinar coming up in the next few months. So I encourage you to join those as well. We will be sending out slides for today's presentation, and on our electricideas.com website, we do have the audio in the file for the previous presentation, and we'll post this one on there as well. So thank you again for attending. We hope you found it useful, and I'll turn it back over to you, Mike, and then Christina, and we can close out today's webinar.
Yeah, we'll have one last webinar here, and then we're going to take questions. This is just a value question about the webinar today, but we have a couple questions, and one of them related to rebates. Jason. So are there any maintenance activities that are eligible for rebates, whether it's coil cleaning or replacement of fan belts or anything like that?
So specifically preventive maintenance, any type of work that's done preventive maintenance, we do not offer an incentive for that. However, I'll caveat that by saying that if there is some repairs or replacements that you're going to do to your system, I would still encourage you to engage our team. We have an engineering team as well that can support your project, and there may be an opportunity to incentivize. I don't want to turn you away before you even submit. Traditionally, just a PM, traditional PMs, though, would not be supported with our incentive program. But if there's any repairs that would improve some efficiency or add-ons to your system that would encourage any efficiency gains, then I would definitely ask you to engage, submit an application, or even get a hold of our team, and we can try to address those. And there possibly could be an incentive for that.
Okay, fair enough. I got a question here about how does eddy current testing work? And eddy current testing is just one of several ways you can find surface defects in metals. It particularly uses a probe that has a coil integrated within it, and the current passing through, the alternating current passing through the coil creates an alternating magnetic field. And as that probe approaches the metal, in this case metal tubes, it will induce a current flow through that metal. And when there are surface imperfections like cracks or something, it'll interrupt the flow of that current in the metal. The coil will get feedback on that and pick that up, and you'll be able to see on a screen. You can't see anything visually looking at the coil and the tubes, but on a little computer screen, it will indicate, oh, there's possible cracks here. And so it's a technically non-contact way using electronic probe to find any cracks on the surface. Now, other ways you could do that would be like a dye penetrant test. Of course, that you have to probably do a lot of cleaning on those coils before you can do that. So when you get to older coils and a fair amount of scale that's difficult to remove, it becomes a lot more difficult to do that. So eddy current testing is a pretty good way to do that. It's more expensive than, say, a dye penetrant type test, but it is also more sensitive as well. So, let's see. Do you have model numbers for belt tensioners? Let me see if I actually do on that. I just had available right here is it's either a Browning tension gauge or a Gates tension gauge. And if you Google that, you'll find those on there. They're pretty similar. They have little fingers jutting out from the center of the gauge, and then the gauge has a little probe that hits the belt and indents the belt a little bit, and gives you an idea of what that belt tension is. So it's either a Browning tension gauge or Gates tension gauge. I don't have an actual model number, but you'll find choices there if you just Google those. So question here on any idea on air makeup units. Again, they have dampers, they have fans, so your typical checking belt tensions and bearing operation. Make sure that it's not unbalanced, etc. That dampers are working. You'd be surprised how many dampers where the linkages, have literally fallen off, and nobody knows. It's stuck in one condition. So So there's some things there.
Hey, Mike.
See here. Yeah.
If I can interrupt real quick, we do offer a $100 incentive under our prescriptive program if on any of those HVAC fans you don't have an existing VFD, and if you're adding one, if it makes sense and it's applicable in your scenario, then we do offer an incentive based upon horsepower. So anything from 1 to 20 horsepower, adding a VFD to an HVAC fan would be a $100 rebate. So there are opportunities as well under our prescriptive program.
Yeah, that's a fantastic upgrade. And again, VFDs are optimal if you still need to operate at rated flows and speeds a little bit of the time, like 10-15%, but most of the time you can back down and run at less than 85% of rated speed. You'll get tremendous savings. A 20% drop in speed gives you about a 50% decrease in energy consumption. Now, it's not going to help. It's not going to help decrease your peak demand because, again, you often run it at peak load sometimes, and that's going to contribute to the total peak. Maybe you get lucky and not hit that exact peak that all the other equipment's running at, but typically you do. So great energy consumption testing. So I had a question here on cooling tower maintenance and just any other tips on particularly doing that safely, because cooling towers are dangerous. I've been in them inside. They're slippery, they're wet. The railing isn't always in great condition. So before maintenance begins, you want to make sure that all safety precautions are communicated and followed according to OSHA, Occupational Safety and Health Administration regulations. And some potential dangers might be if you have a cool roof, which is typically white. You won't think about this usually, but it can really reflect blinding sunlight. Polymer-based roofs, they're often slippery when they're wet. If you're doing this, which you often are in the winter time, black ice can form on roofs, increasing the possibility of falls. And I've even seen situations where lightning rods attached to rooftop cooling towers pose an impalement hazard. I mean, if you trip, fall, stumble, those are really sharp rods, often really close to the edge of the top of the cooling towers, etc. So you also want to make sure that OSHA rules for railing along elevated crosswalks are followed. You want to wear a breathing mask. It is not unusual to hear technicians say, hey, I'm not going in that cooling tower. I mean, it's Legionella possibility. And so you want to take proper respiration protection as well. And then also note that if the tower only has one door, it could be classified as a confined space per OSHA rules, which brings into a lot of other challenges in terms of having a lookout, having extra air pumped into that space, et cetera, et cetera. So just be aware of that. Might want to check that out as well. So how much time we got here? Getting toward the end here. Okay, I had a question here just about that root cause analysis I talked about. Let me go over to that one. Show you we had that. Let's see if I can find it again here. It's right at the beginning here. Here it is, I think. Let's see if that's it. Yeah, here it is. So what we're talking about here is the 6 M's. You could have human error, faulty judgment, lack of knowledge or training, just human fatigue, or a medical condition that would cause things to not be maintained the way you want them to be. That's the man category. The second category, method, you might have the wrong sequence of operations. Again, it's not very typical, or improper method of reading, let's say, refrigerant levels or other values. The machine category might be an undersized motor, use of a fail-open valve instead of a fail-closed valve, or not using a proper belt tension tool, which you've all been asking about. The materials category might include clogged filters or adding polarized refrigerant oil that clogs heat exchangers. The measurements category might be a building automation system deficiency or a spurious signal coming from a sensor, maybe trusting that dampers are shut when they're not, which we talked about. And the Mother Nature category could be excess humidity or rain, for instance, that's causing this unusual maintenance condition. So just some things to think about when you're trying to diagnose your maintenance issues. Well, we've come to pretty much the end here. Let me see if there's any other questions here. Let's see, there was a question about rebates for VFDs and chilled water and condenser water pumps, and I think Jason addressed that. If we didn't get to your question, we'll answer that offline here after the webinar is over, so be rest assured we'll get to all of your questions here. With that, though, I'm going to turn it back over to Christina for some final closing comments for today. I appreciate your attendance and participation.
Great. Thanks, Mike. I would just like to thank you all for attending our webinar today. As a reminder, the presentation materials and the playback link to the recording of today's webinar will be emailed to you sometime within the next couple of days. If you do have any additional questions or feedback, please do not hesitate to contact us. And thanks again for everyone for attending, and hope you have a great day.